Hello, everyone. I'm going to start talking about marks and channels. That is actually the next lecture after the initial talking about visualization design guidelines. I was right in the last lecture. Marks and channels. These are the things that you've been seeing in Tableau. You've seen in Altair. You've seen it in a lot of other contexts. It's actually something it's relatively new to me. Not new as in the past year or two, but not 20 years. It's part of the language that visualization designers use that you have to sort of get your head around. And so let's go over the individual parts. So first of all, just a quick review. Tufte likes dated ink ratios, hates chart junk, and has a whole bunch of rules about basic design visualization designs for visualizations. And we looked about visualization critiques. You also notice I balked at some of the Tufte's ideas from time to time, but generally they're very, very good. I just think there's a bit more nuance than he gives it credit for. So if you want another example of a visualization critique, here you go. The Code City critiques. This is a visualization of code. It could be almost anything, but the initial use case is code repositories and different packages of the code. I hopefully have a mouse. Here you go. Packages of code. Within the package, the size of the individual, the amount of code itself is based on the rectangle. The number of commits would be the height. And you get a sort of a landscape of a code repository to see who's making changes or where changes are being made. If you wanted another example of how to do a critique, this would be a good one. Love to hear your opinion on it. You don't have to pass it in or anything like that, just in case you wanted more practice. Okay, so for today, we're going to be looking at the various primitives in a visualization, the marks and channels. And we want to understand how we break down these complex visualizations into these marks and channels components, and how we assemble them back together to make a visualization. And we'll figure out why some marks and channels are more effective than others for a given task, like perceptual ordering, and we'll discover why Tableau and Altair keep using these terms, essentially because this is where the field has been using them, or that the field has been using these. So, a Hall of Fame and Hall of Shame as usual, of course. This is from XKCD. You might think lots of chart junk. I'd like you to have a think about what this is actually trying to indicate, and is it actually very effective? It's essentially a scatter plot. So I like this visualization, or bringing up this visualization, because it covers marks and channels so well. These are actually particular kinds of marks. It is a fame, despite the fact there's all of this extra cruft involved. You didn't have to use images of everything, and the data set itself is just silly, but it clearly conveys what you're trying to get across quickly, and you know exactly what you're seeing quickly. The actual marks being indicated, the categories and the various types of fruits really pop out quite nicely, and it's quite funny. So I think it's well done. Here would be estimated heat accumulation from the New York Times, and how much heat is, I think, to cause how much heat is in the ocean versus in ice, land, and the atmosphere, where it gets trapped essentially, and whether this thing is done well. Again, a marks and channels thing. I think that's really quite well done. And despite all the extra cruft in there, like the misery map, this whole banner up here, this would be a visualization of where people had cancellations, delays, and which airports and how much of a problem they had in each of these places. And you could see it over time as well. Nice, huh? And you can see what, so the size of the airport and the number of passengers will be based on presumably the size or the area of each of the circles, and then the percentage of cancellations versus flights that are going well are indicated by the donut chart. So the red is some kind of misery. I thought it was really well done. You can actually look at this yourself, the misery map, and see see if you agree with some of their findings. I love the fact that it's very accurate. LAX is a piece of garbage. I hate LAX. Having been there a couple of times, just no, it's a bad airport. And Seattle is actually really quite nice, so that's up there. Okay. And Boston, yay! Boston's not doing too bad for a bunch of really surly people in my town, former town of Boston. They're doing okay for their airport. Okay, let's go to Marks and Channels, because that's actually what we were doing there. So these are just our basic building blocks. It gives you a language to describe a visualization. So a mark is a basic graphical element. So this could be a whole bunch of different things. It could be points, for example. It could be lines. It could be areas. Heck, it can be text. It can be more than just these three. People keep on pointing out these three, but it can be things beyond that. It is something that I can manipulate to convey data. And those are often points or shapes, but they're effectively a point, like the fruit. There are areas which would be that heat, where heat is being trapped, is actually an area because it's a stacked graph. Now you could consider it a line based on where it goes as well. It depends on where you want to slice and dice this thing. The donut charts and the previous illustration, though, are areas for sure. A channel is the way you can control the appearance of the mark. So it's independent of the dimensionality of the geometric primitive. So it allows you to, the channel allows you, it's what is controlling the geometric primitive versus the mark is actually the geometric primitive. So hopefully we have a nice little example of this, and if we don't, I'll find one. Okay, so the channel might be the position on the screen, or both, right? That would be one channel. The color is a channel. I can encode different things with different colors, or I can use color to show the have a white to dark blue, for example. So have a color gradient and show continuous data that way. Or I can do different hues and show categorical data. I can do different shapes. Great for categorical data. Terrible for continuous data. I can do tilt. And you've seen tilt before. That's a pie chart, technically. Now you could say the amount of the area, but really what you're seeing is the edge where the two edges are, and that's the amount of tilt of the line as well. You can argue that a pie chart or a donut chart, both would be the same. Both use tilt to actually encode that data, which I find weird. You can use the size, the length of the line, the area of a square, the volume of a cube. All would be the size of something. They're all ways of encoding the data. It's still a line, no matter what. Here, there are three lines. Where's my mouse? Let's use a pen. There are three lines here using different colors. There are three lines here using different lengths. They're encoding different things. I could change the color and the length of the line. Two different channels. But the mark is still a line. Or I can tilt it as well. So, as they're building blocks, let's have a look at a couple of these things. So, what are the marks in this? And what are the channels? So, I'll walk you through one. So, what are we encoding? We have some kind of thing on the x-coordinate, and the x-axis, presumably. And we have data being encoded on the y-axis. Normally, this would probably be independent variable and a dependent variable for the y-axis. Okay, but may not be, but we effectively have two dimensions, right? Two-dimensional space. It's a two-dimensional graph. The mark, what is the mark? Well, you could either call it a line or you could call it an area, because the areas are changing. The size of the areas are going to change because of the height, but the width of those bars don't change. So you could also consider it a line if you want, because it's just a big, fat, thick line, depending on how you want to view it. As long as you justify what you're saying, you're good. It's not a point. It's either a line, because I'm only manipulating this shape in one direction, one dimension, along the y-axis. So it's either a line, which is really thick, or it's an area, which only goes in one dimension. Both fine. Oh, sorry. Versus a channel, what do we have? Well, I have the position of the bars, which actually makes a difference, right? It is technically both. I am moving it along the x-axis, and where their position on the y-axis tells me something. But you could also say it also has a different length. I am not changing color at all. I'm not changing shape at all. I'm not changing tilt at all. I am getting the length or the amount of area, both at the same time, depending on how you want to view it, as well. So I'm encoding two different things. I have two different channels. I have position, and I have either size or area, but I have size, length or area. I have size, and I have position as my two, encoding my two dimensions. How about this? What am I encoding here? Well, actually, it should be the same, almost the same thing. Those are clearly points. So number of attributes. I have an x-axis, I have a y-axis, two dimensions. I clearly have points. I have position in space. I got nothing else. At least I can't think of anything else that I have in there. We're done. Now, I can encode other dimensions. Well, I have a third dimension in here. Technically, I'm encoding, we're using color, some other attribute. There's actually three things here. I'm still using points, and now I have hue for my color, or color, the hue that's changing to indicate something, like a category. I can do one step further. I can use the size of, or the area of these circles to indicate yet another dimension. There's actually 4 dimensions being represented here, and I have to throw one more thing in here, which is the area. How about this? How many dimensions are being encoded with a pie chart? Well, technically, you could say that color is encoding different categories of information, but they're also being spatially laid out. Okay, what else do you have? You can either say the size or the volume of the pie pieces, but you can also say it's the tilt, because that's actually, you're not seeing this entire area, you're gauging the distance between this and this. You're seeing this thing here. You're comparing two tilts, perceptually at least. So I'd say there is one dimension or one attribute. There are 4, there's 4 different data points or 4 different objects or items that you have there, but there's only one attribute being encoded, which is the size of the pie. It's using areas. The colors are indicating the different pieces of the pie. It's actually not encoding an attribute. It does have color though, I'll give you that, fine. But it's tilt. The color will indicate the different, which piece of pie you're dealing with, but yeah, tilt. We also have the area. We could call it the area, but area and tilt, they're both encoding the same thing. And again, I have one attribute. That's it with a pie chart. Hey, donut chart, same thing. Here we go. It's an area. Great. I have color. I have tilt. I have area. How about this? This is a matrix, or call the heat map actually. Not the heat map where we're looking at things, although they're related. So I can use lightness to darkness to indicate a particular channel, and I also have where on the grid. So what do I actually have here? Technically, I have 3 dimensions. I have a dimension on the x-axis, I have a dimension on the y-axis, and I have the intensity for each of those cells. The cells themselves, you can call them areas. I wouldn't call them points, although they're all uniform in size. You could argue it, but I would call them areas myself. I have position in both dimensions, and I also have color. It's black and white, but it's still color. I'm using the luminance to change things. I don't think I have anything else. How about this? This one is bonkers. So this is a tensor shape. So we are using the shape of the object in multiple dimensions going along the x, the y-axis, the y-axis, also parts of the triangle, I believe. You also have the different level of shading on this thing, and so it goes fatter in this direction, it goes flatter in this direction, and it goes thinner on this direction, or it actually fattens out in a different dimension the other way. Turns out there's actually and then I think the level of luminance or brightness on this thing. You can technically encode 4 different attributes in this set of tensor shapes. And let's see what we have here. Do I have that? Plus position in 3D space. We technically have points, and we're manipulating those points in rather large ways. We have both x and y coordinates. Yes, see, there's x and y coordinates as well. We have x and y coordinates. We have tilt. I don't think color is actually being used here. That's a shading effect. We have the amount of tilt that's on this thing, and we have the length of these things that it elongates, and we may have area as well. No, volume. Sorry, it's a 3D shape. Yeah, it's encoding a lot of stuff. As you might imagine, it's not immediately obvious or readable. But if you're an expert in this field looking at these sorts of things, maybe you're faster at reading these things than I am. I certainly am not fast at reading these things. Oh, there's also different shapes that automatically come in there. Forgot about that one. There you go. Here are another series of super quadrics, which is a tensor shapes. I'm not even going to pretend I understand any of this other than the fact I'm saying you can pack in a lot of things in a grid of tensor shapes where your position, your shape, and how you manipulate each of those shapes differ, and you can really encode a lot of information, but it's not obviously intuitive or necessarily obvious or intuitive. But how about this? Here's a brain scan, and they're using tensor glyphs, if you will, tensor shapes, to indicate blood flow through the brain at various places. You do not have to read each individual part. Instead, you get a sense of where high blood flow regions are going through. You get a sense of the number of, or maybe this is neurons firing. You get a dimensionality, you get directionality, you get flow of things. You get a general sense of how the brain is actually working with a bunch of tensors. Okay. I like node link diagrams, so I drew up a node link diagram as well. Notice that my node link diagram, I have a series of points, technically points. I have a series of lines, and I can manipulate those things and do a lot. And then, I can also encapsulate part of this. This is a click or clique, depending on how you want to pronounce it, where all the nodes are all connected to one another. And I could identify all of those together by, encapsulating them all, putting a circle around them all to indicate that. Well, that's a whole lot of different marks, so I have all three different marks, and I have a whole lot of attributes being encoded by different channels. I can change what each of those nodes look like. I can change what each of those lines look like. I can change the color or the shading or the texture of the areas that I'm doing. I can do a lot of different things. But notice what else I have with a node link diagram. I'm indicating connectivity with lines, not indicating necessarily direct data. It's just connectivity. I can also indicate containment. These are the elements that are contained in this click. Containment using area. Marks are not just for the items themselves. They can indicate other things like containment, like connection. These two things, the connection is between this tree node and this tree node, right? Or this node and this node. And position can actually be encoding in this case, position is actually encoding the hierarchical position. Marks as links come in handy in all sorts of different places. So here is, what is this called? I always blank on this thing. Rubber band chart. I'm trying to remember what it's called. Or we can do a tree map. We can do a normal traditional hierarchical tree data structure. We can do a graph. We can do all sorts of things. But notice the lines are indicating connectivity, including directionality of that connectivity right here. Right? The width of the arrow indicating the amount of connectivity. You can actually encode a whole bunch of different dimension or attributes within these things, even if it's just showing connections between nodes. So when it comes to making your visualizations later, I really expect people to break out this and come up with conclusions on how you designed it, what are your marks, what are your channels. That's the language I'm expecting you to be throwing at me. I'm expecting that language when you're doing your data critiques. You use this for your marks. You use this, that your channels were encoded using this. Or these were your channels encoding these attributes. So marks can encode nodes and items. They can also encode how things are connected together via containment or connection. And here are the various channels that you have available to you. There's probably more channels that you may have. There are definitely more marks in this, more than just points, lines, and arrows. Text can also be that. You change the size of your text, the color of your text. It indicates different things. That's what a word cloud is. So how do I pick which marks and channels to use? Because as you might imagine, you could try a whole bunch of different things. I could try, instead of using a point, I'm going to use a line now. You could just try different things. That's what Tableau is all about. Try different approaches. Try different channels, right? The question is, how do I choose? Well, it turns out that if we want, it depends on what the task is. And your big takeaway is, if I know what the task is and I know who the users are, how do I choose what things to prioritize? Because there's only a certain amount of things you can prioritize. And so breaking down a task into what is critical, what is nice to have, is what we're doing. So it turns out Cleveland and McGill, 1984, yes, looked at this. They broke down all of these kinds of tasks. They looked at all the ways you could encode data via these various channels and looked at how good you were at perceiving these differences. Turns out, so they graphed by position and a graph by angle. So this is the same graph or the same data in a pie chart versus a bar chart. Two different formats. And the question is something like, which is bigger, A or C? Or the question might be, how much bigger is A compared to E? Which segment is the maximum? What's the percentage value? That would be a good better test than I was giving, right? D is clearly the biggest segment. Which one are you faster at reading at? I know I have a hell of a time with this thing here. Even just seeing if A is bigger than C, I can't necessarily see it right away. I think B is bigger than A, yeah. But it doesn't slap you in the face. This is a lot faster, right? So you give people a particular set of tasks and you see how fast or how accurate they are doing those tasks. So here is the thing. They did a bunch of different approaches, and you can look at the paper yourself if you really wanted to. But position takes the top 3 spots in terms of the absolute error here. I'm assuming the further to the right, the worse it is. Position is taking some of our top spots. Position down here is taking a top spot. The angle is pretty darn terrible. Now, not as bad as the length over here, but we'll see where that comes in handy in a second. So, in terms of position, this is what one of the conditions was. This is the other condition, what we just showed you. This is why pie charts suck. They are not very good because we're not good at reading them. We make all sorts of errors with them. So this is another reason why pie charts are bad. They're also, if you make it 3D on top of that, first of all, you're not seeing notice the luminance difference is not there at all. It's a terrible choice of colors. They're 2 different hues, same amount of brightness for both. If you're red-green colorblind, you're probably not seeing that very well, I'm presuming. Here is that same pie chart in 3D. It looks like it's coming out of the board, right? look how distorted that pie piece is over there. Because on your visual feed in your eye, it's a tiny, tiny, tiny bit of blue. The actual bit of blue is much big. It should be much bigger, but it's because it's in a perspective, you don't see it correctly. And all of this stuff, making it look like it's three-dimensional, is actually getting your way of reading this thing. So it's not only 3D, it's a pie chart. Just good God. I made that joke, and he wasn't looking at me at the time, unfortunately. When I was at Google, I was contemplating working with this other team, and he was talking about using a sunburst visualization and a couple other things. I said, hey, how about a 3D pie chart? And just the color just drained from the guy's face. It would have been my future boss. I'm like, I was joking. So, oh my God, I was having a heart attack. It was like he was just about to turn me around and just kick me in the ass, getting me out of the office. It was that much of a cardinal sin. I was purely making a joke. Right? 3D pie charts show that you don't know what you're doing. Personal opinion. This is the only pie chart I've ever loved, and I think it's a great pie chart. I want some of this pie chart. It looks very delicious. So, other than that, try not to use them. And I literally when I was teaching this last term, I literally got someone trying to spam me with like, hey, you should use our program, Click, I guess, KQLIK, for embedded analytics for your classes and all this kind of stuff. And I look at it, and if they're telling me their embedded analytics is pie charts, I don't want their embedded analytics. Thank you very much. So I got a kick out of that fact, because they're trying to trying to get me to buy their product, and the thing they're showing me is telling me do not trust them with their product. Personal opinion, of course, but I think other visualization people are equally willing to take that particular claim. I understand how other people love pie charts. They're just not effective. So if you do love them, fine. Just know that there's a huge cost to using them. Turns out William Playfair from 1801 comes up with an original pie chart, in case you want someone to blame. But maybe you shouldn't blame him, because so here's the initial pie chart that he came up with for the Turkish Empire. But he also invented, the bar chart. He invented this particular graphic here, which is huge. I think he may have been line graphs as well. I can't remember. He's this huge, innovator in the field. He did all pie charts, area graphs, line graphs, and bar charts. So he's a slacker. So here is the point of all of this. If I only have a couple dimensions I can show, I better make them count. So knowing what the task is tells me how I need to present things. And this is what you should be critiquing people with when they give you a visualization. That if they give you a pie chart, you can crap on their pie chart, fine. We already did that one. But here is, I'm really, really good at comparing two bars next to each other. I'm not so good, but if they're as long as they're aligned, bars next to each other with some extra interruption here. That's teeth 2. So this orange and this blue, can I compare them? I'm wondering where the blue is. I think it's here and here. So we're not as good, but we're okay comparing across different clusters with things in the way. We're pretty terrible if they're misaligned, right? If they're both, these are both at the top of their bars, but on top of that, they're not in alignment with each other, so they don't have the same base case. My wife hit one of those cases with some of the graphs she was trying to show, and I was like, yep, they're not, your axes are not aligned, it's going to throw everyone off. And where you're really terrible is when things are completely askew when it comes to comparing sizes. Turns out, here in Bostock, the people invented D3 also did this in 2010, and they use the Amazon Mechanical Turk system, and they compared how people do for these same sorts of things in 2010, so more modern context, and had hundreds and hundreds of people comparing these things, and pretty much found the same results. So the top spots almost across the board are positional. After that, Then we get angles are okay. After that, circular areas are not very accurate. In case you want to give me circular areas, we're pretty bad at them for accuracy. Now, this one's bigger than this one, we're okay with that. Rough approximations, we're okay with that. But if you want to read off a number or be accurate on which one is bigger, they're pretty terrible for that. And rectangular areas that are not aligned, so tree maps, for example, which everyone loves tree maps in my field, but they're terrible for reading things off of. It's one of those. Some people were so big fans of tree maps. I've always bashed them, and this is showing that they're not very effective for visualization tests. So now you need to choose. As effectively, you have to choose. You have to pick your poison. You have to choose what you're willing to give up for your system. So you need to know what the task is, to know what, because you'll have more data than you can show. So if you have these bar charts, what you really want is, if you need to compare these two, the red, the orange and the blue here, you better have them right next to each other. If you're not likely to compare them, maybe put the blue here and the orange one over there. That would have been fine. If you put them if you really need to prioritize direct comparisons, though, side by side. It's all about, there are some things that are better than others for comparisons, and you're just choosing what's the most important thing. I keep on forgetting to remove this thing here, so hopefully it'll be removed now. No, it will not remove now. So, in terms of expressiveness, how good we are at reading these things, position on a common scale is fantastic. It's one of our best things. Position on an unaligned scale, not as good. The length is pretty bad. It's okay, at least. Better than tilt, for example, which is better than the area, which is presumably better than the volume as well. The depth in three-dimensional space, we're pretty bad at that one, even with 3D effects. The color and luminance for channel ordering and magnitude, pretty bad. You can still do it. If you want to convey that information, you can do it with color. It's just not very good for accuracy of reading that off. Curvature is even worse, and volume just stinks. We're really bad at accurately judging that, because unless they're all cubes. If one's a rectangle and one's a sphere, it's really hard for us to judge that. For categorical data, spatial region is really good for different categories. Color and hue is fantastic. So color hue, not color and hue. So colors of the rainbow, great for categorical data. Motion is fantastic. People hate it, but it's really good for categorical data. Shape is really good. We'll see that all over the place. So if you're trying to encode categorical data, you stick with the stuff on the right. If you're trying to show ordinal data, you stick with the stuff on the left. And you prioritize it based on the task that you're giving people. What do you need people to be able to do? That's the task you want to get. That's the way you encode your information. In terms of expressiveness and effectiveness, it's a different term. This is from Jock McKinley in 1986. The expressiveness, let's do effectiveness first, sorry. Effectiveness principle is that the importance of the attribute should be match the salience of the channel. So if it's a really salient channel, if it's a really good channel, that's the important attribute, that you put the important attribute there. Okay, that's pretty obvious. I just said it about 4 times. So it also was obvious probably before you got to class. In terms of expressiveness, the visual encoding should express all of and only the information in the data set. So the data should match the channels. You shouldn't be using hue for ordinal data, for example, or for you should not be using hue for continuous data. What you end up getting is, if you don't use the right expressiveness or choose the right channel for expressiveness, people will read it wrong. So prioritize the most appropriate channels for each attribute and choose the right one is the big takeaway. And you just got to take a long time sitting down thinking about, what's my channel, or what's my priority task? What channel should I use? It's not necessarily just off the top of your head, you improvising, you're making crap up. You methodically go through your designs, figuring out what's the channel, what's the marks, what's the channel, and what's the max, how can I maximize or make the most salient channels encode the most important information. This would be, by the way, the expressiveness would be, this would be an example of doing the expressiveness wrong. So car nationality, right? What's the best cars? Well, it turns out Sweden is fantastic cars, and I think the Volvo is the best car, and so is the Saab. Wait. What is this actually encoding? Because le car, if you've ever seen a le car, you'll know it is not one of the best cars in the world. It just happens to be made, in France. Same with the Peugeot. Why? Because that is actually the better way of encoding this. Here are the German cars, here are the Japanese cars, here are the American cars, here are the French cars, here are the Swedish cars. This says better or worse because if it's a bar chart, we naturally read it that way. Even when we know, even knowing that it's not showing which car is better, I still read it as which car is better after all these years. That's the better way of doing it. The encoding of the data makes more sense in this case. The expressiveness is there and the effectiveness is there as well. Okay. I don't know if I have, what else I have in there. So here is the summary of all the different channels. What I would like to make sure that you guys do from now on is when you see a visualization, break it down into marks and channels. Figure out how you can encode things. See if you have two attributes or one attribute being encoded two different ways and there's really no need for that, let's say. Like, for example, the Code City visualization. There's a redundancy of the encoding of information there. Where is it? Is it the best choice of marks and channels? That's why I gave that example. It's pretty terrible for that, actually. So have a look at it again. Look at the marks. Look at the channels. How are they encoding data? Like, we have bars there, essentially. There are actually volumes technically, but you can consider it an area and then a height as two different dimensions. But even then, it's pretty terrible. So, okay, I'm going to take my leave, and then we're going to pick up, I do believe, with another, I think maybe filtering next class. All right, thanks everyone.